So moving on from looking yesterday in relation to water treatment, we looked at the treatment of water before it comes to the house and the treatment of water after it comes back from the house. And they're both different treatments. One, I think the best way to sum it up is when you're getting water sent to the house, you're taking it from a natural resource and you're cleaning it, making it fit for human consumption. Okay, that's the first stage. The second stage then is after it has been consumed and used, it is then discarded out of the house and it must be treated for a second time before it's returned to nature. So nature, house, nature, house. It's got that kind of a cyclical process, and that's why water is treated twice. You can't take water into a house unless it's clean and fit for human consumption, and you cannot discharge used water back into nature again unless it's treated and released in a way that's not going to harm the life that depends on that water. So we're just going to take a look at a thing called hardness in water today. It's a phenomenon that occurs in most of this particular country, normally where limestone regions are. And hard water, it's not ice, by the way. Don't write that down. What is hard water? Ice. No, it's not. That's frozen water. Hard water is water that contains calcium or magnesium ions. End of story. Okay, so if there's trace calcium in your water or trace magnesium in your water, it's discovered or it's determined to be hard water. And normally water that is involved in limestone regions is described as being hard because that's where it gets its calcium and its magnesium from. So it's caused, as we said already, by the presence of calcium ions or magnesium ions dissolved in water. When we have hard water, people who know what hard water is and people who've come in contact with hard water before will tell you that when you use soap with hard water, the first couple of minutes trying to use the soap with the water doesn't produce any suds, doesn't produce any bubbles, what we call a lather, okay? In fact, what's happening there is pure chemistry. The soap itself is a compound called sodium stearate, and there's the structure of it there, okay? C17H35 COONA. Now, as we know, under normal conditions, soap is soluble. You use a bar of soap, it goes down in size, okay? But if you introduce water that contains calcium or magnesium, what happens is the calcium and the magnesium that are present in the hard water replace the sodium. And in fact, they turn what we call the sodium stearate into calcium stearate or magnesium stearate, as the case may be. And the difference is that whilst sodium stearate is soluble in water, magnesium and calcium stearate are insoluble in water. So this chemical reaction takes place where the sodium stearate from the soap meets the hard water containing calcium and magnesium. There's a swap of sodium for calcium and magnesium, and what ends up in the water is the calcium stearate, which floats to the top as a kind of a skin, okay? It looks dirty. We call it a scum, but it floats to the top as an insoluble precipitate of what we call calcium stearate or magnesium stearate. The soap produces a lather then when all the calcium ions are used up. So really what the soap is doing is it's removing the calcium from the hard water, it's forming a scum which floats on the top, and when all the calcium is gone, only then will the soap begin to do what it was supposed to do, designed to do, and that is give you a lather and start to clean things. Hard water is common in regions which are rich in limestone. Now I just want to take a moment just to draw this out crudely before I get into the chemistry of the equations that are going to appear in these slides. So basically, if it's common in regions rich in limestone, what you'll notice is that there's normally caves in limestone regions. Okay, so you've got your stalagmites and your stalactites like this, stalagmites and stalactites, and out into the sea. So we'd say that's the sea coming in here. Okay. Now, let's just take a couple of steps in relation to how does calcium and magnesium get into the water in the first place. Well, obviously, there is evaporation. And evaporation, as we know, is the process by which the surface layer of water molecules get enough energy from the sun itself just to lift off into a vapor form. Okay, so we get evaporation thanks to the energy from the sun. So there's your evaporation. Now, when that vapor rises high enough and cools down, what happens to gases when they cool? They condense. And when they condense, they obviously form clouds. Okay? And as they continue to condense, the clouds get heavier and heavier and heavier, but they also get darker and darker and darker. So they get heavier like this. The amount of water droplets begin to congeal, to get heavier. And eventually what will happen is that the rain will begin to fall. Okay, and that's what rain is. Now, here's your first piece of chemistry. Number one, as the rainwater falls through the air, it dissolves the naturally occurring carbon dioxide, and the two molecules fuse together to give you H2CO3, which is a dilute form of carbonic acid. Now, carbonic acid is a weak acid, okay? So you've got a dilute weak acid. When this dilute weak acid hits the limestone region, we get the second piece of chemistry taking place, where your calcium and your magnesium that's in here, your H2CO3, meet your limestone. Now we're just going to take limestone as CaCO3. And what happens there is that both of these combine and they give me what's called calcium hydrogen carbonate, CaHCO3 twice. Okay, now that calcium hydrogen carbonate is soluble. And what that does is it trickles down drop by drop from the cave into the cave itself. And from the cave then it moves back into the sea or into the river, whatever's beside it, and that's how the calcium gets into water. Okay, so there are two stages in getting your calcium into water. Number one, the production of carbonic acid by the addition of rainwater and carbon dioxide, which is naturally occurring in the air. So therefore, rainwater is naturally going to be acidic anyway, okay? And then the second piece of chemistry is when that acidic rainwater hits the calcium carbonate, which is the limestone in the limestone region, they will undergo a chemical process by which they bond and they form molecules of calcium hydrogen carbonate, which is soluble. So that is how the insoluble calcium carbonate enters into water as soluble hydrogen, calcium hydrogen carbonate, and then enters the water supply this way, and that's how it gets to your home. Okay, so that's a very quick demonstration as to how it happens. So keep that in mind. It's a two-stage process. First of all, the first piece of chemistry in the air, the second piece of chemistry in the rock. Okay. Rainwater, as we said already, is slightly acidic because the rainwater and naturally occurring carbon dioxide form carbonic acid. Okay, now carbonic acid is a weak acid, but still it does the job of dissolving the limestone. It reacts with the limestone to form soluble calcium salts, which we call calcium hydrogen carbonate. Now, if you ever had the misfortune of leaving a bottle of vinegar on a marble fireplace, the same thing happens. If you put a bottle of vinegar on a marble fireplace and the vinegar dribbles out onto the marble, vinegar is a weak acid, it's ethanoic acid, okay? It's a solution of ethanoic acid in water, but it is able to actually physically dissolve the marble and leave a permanent ring, okay? Here we're doing the same thing. We're sending naturally occurring acidic rainwater down through limestone regions where the acid rain will dissolve the calcium carbonate and form calcium hydrogen carbonate, which, as we say, is soluble and enters the water supply that way. There are two types, and I think you might have done this in your junior cert already. There are two types of hardness, okay? There's a hardness that can be removed easily, and then there's a hardness that is more difficult to remove, okay? Now, both of them are removable. One is easy, one is more difficult to do. The one that's easy to remove is hardness that we simply call temporary. So in other words, it's there until you do something to it. So the water will be hard until you do something to it. And the simplest way to rid ourselves of temporary hardness is to boil the water. Now, in doing that, what we actually do by boiling water containing calcium hydrogen carbonate or magnesium hydrogen carbonate is we undo what nature did in the previous step. Think what happened. Carbon dioxide and rainwater in the air formed carbonic acid. Carbonic acid fell down on the limestone region, the calcium carbonate, fused with it and formed calcium hydrogen carbonate. So therefore, when I heat either of these two, the whole natural process that happened in the limestone region is undone in a couple of minutes. Meaning this, your calcium hydrogen carbonate, when you heat it, simply decomposes itself back into CaCO3, the rainwater that fell from the clouds, and the carbon dioxide that was in the air. Okay, and if you look and see, that's already balanced. One Ca, one Ca, one CO3, one CO3. What have you got? CaHCO3 twice it should be. So you've got two CO3s, I should say. So there'll be a 2 there. Remember that correctly. Ca and Ca. Did I do it right? CaHCO3 twice. Calcium hydrogen carbonate. Yeah. So there'll be 2 CO3s, 2 calciums. So let me put a 2 in front of that. All right, CaCO3. Ah, sorry, CaCO3 and H2O and CO2. That's my mistake. Let's go back there again and take that out. Don't need that at all, because I'd forgotten. You've got your CO3 twice. You've got your CO3 there and your CO3. So you've got 2 CO3s. There's one of them, and there's the other one. Okay, I forgot it was at the other end, trying to balance something that was already balanced. And then you've got 1 calcium, 2 CO3s, 2 CO3s, and 2 H's. So the whole thing is balanced. But what you've done is you've taken something that was formed in a natural process of weak acid carbonic rain falling down onto calcium carbonate, forming calcium hydrogen carbonate. When you boil it, it undoes that process. It gives you back the calcium carbonate, which is the limestone. It gives you back the rainwater that fell from the sky, and it gives you back the carbon dioxide that was in the air. Now, here's the key thing. What happens when the calcium carbonate reappears? The answer is it forms a solid that we call lime scale. And this lime scale that appears when you boil water containing temporary hardness, this lime scale causes all kinds of problems. Number one, it starts to reduce the size of the insides of your pipe. It builds up on the inside of your pipe, a bit like how cholesterol builds up on arteries. Okay, it begins to stick to the walls, and it narrows the pipe through which the water flows. That's the first thing. The second thing is it also builds up around heating elements. So if you're in a limestone region or a hard water region, and you boil your kettle, you'll notice that the lime scale begins to deposit itself over the element, meaning that every time from then on you try to use your kettle, it becomes less efficient. Likewise, it does the same in a burner, it does the same to all your utensils, so it just damages equipment. Okay, it's not a good thing to have in relation to equipment. However, hard water is a good thing to have in terms of human health, because it contains calcium, and calcium is good for your bones and good for your teeth. So there's a kind of a balance between, do we get rid of all the hardness, do we not, do we leave some in? That's up to individuals. A lot of people, because of the damage that it causes to washing machines, you know that ad, the Calgon ad, and your man goes up and he opens the back of the machine, he takes out the element, and the element is crusted in limescale. That's what's happening. Hard water in your machine being heated, decomposing down into calcium carbonate, which is limestone, which then sticks to the innards of your machine and makes them inefficient, or eventually breaks them. Okay, so let's take a look at this. These salts are unstable, and they will decompose on heating, leaving the water soft, meaning that the soluble calcium hydrogen carbonate will decompose simply under heating. That's all you've got to do, just heat it, and it will go into calcium carbonate, CO2 and H2O. Those two will be lost to the atmosphere. But this one here, notice the arrow downwards, this is what we call lime scale. And that's what poses problems. The CaCO3 that precipitates is a substance called limescale, which builds up on the inside of hot water pipes and tanks, as well as kettles, etc. So there's an example of where the original pipe has now been filled in layer by layer by layer by precipitation of calcium carbonate. So the original pipe, if you notice, was there. There's the original inside of the pipe. See that? And that's what it's been reduced to. So it does do damage. An easy test to carry out on scale is to simply drop some dilute acid on it. Now, if this is scale CaCO3, if you drop any type of acid onto it, say HCl, what will happen is you'll get CaCl2 and you'll get CO2 and H2O. Okay, so in other words, you'll have carbon dioxide given off. In other words, it'll fizz. Okay, so that's what happens. Doesn't matter what acid you put onto calcium carbonate. If you scrape some of this thing off here, add acid to it, we'll notice it'll fizz. And if it fizzes, then you know what you have is calcium carbonate that has come from the water supply in that particular region. So we put a 2 in there just to balance the whole thing. Okay, this will come up in the slides later on. The acid reacts with the scale and it fizzes, because calcium carbonate with any acid will give you carbon dioxide and water. It's not really interested in the salt. That's the salt. We're not really interested in that. We're interested in this thing here, because that'll fizz. And as it fizzes, we then know that the scale came from the water in the limestone region. Permanent hardness, on the other hand, is more difficult to remove. Okay, so what do I do with temporary hardness? Temporary hardness, I boil it. What happens? It breaks down, disappears. Okay, causes lime scale, but the water itself becomes soft. What about permanent hardness? Now again, it's hard because of the presence of calcium and magnesium, but it's permanent because the calcium and the magnesium are no longer hydrogen carbonates but sulfates. Now this is where you start to move into the leaving certificate aspect of hard water. So temporary hardness is due to calcium and magnesium hydrogen carbonates, which are broken down easy by heat, whereas permanent hardness is due to calcium and magnesium sulfates, and sulfate is a very, very stable radical, and these are not easily broken down by heat. So in other words, if you boil water and it remains just as hard afterwards as it did before, then you know that you're dealing with permanent hardness. You know that you're dealing with the sulfates of either calcium or magnesium. It is not removed by boiling, but by 3 other methods. Number 1, distillation. Now, we very rarely, even in the lab, build a distillation apparatus anymore. Okay, it's too expensive. It's too cumbersome. So could you imagine if you were living in a hard water region, could you imagine having to have a distillation apparatus out the back of your house that was able to take care of your daily water demands? Totally impractical. So whilst distillation will remove the hardness, it's not a practical method to do it. Okay. Ion exchange resin, which I'll look at in more detail in a moment, is perhaps the way that most houses now tackle hard water problems. And what they simply do is they suck out the calcium and the magnesium and they shove in sodium. So they take out the ions that cause the hardness and they replace it with an ion that doesn't cause hardness. Or, lastly, washing soda. Now, washing soda is sodium carbonate, Na2CO3. And what we can do there, if we add that into hard water, let's say, for example, water containing CaSO4, here's what happens. The sodium replaces the calcium completely, and you end up getting sodium sulfate, which is soluble in water and doesn't cause hardness. So these are what we would call exchange mechanisms. The distillation isn't. Distillation is a removal mechanism. You basically boil off the water, you collect the water, and you leave the impurities behind. Okay? Whereas ion exchange and washing soda, they physically remove the calcium and the magnesium and they replace it with sodium. And that's what I want to look at, the chemistry behind these two now. So here's an example of one type of ion exchange resin. I don't know whether you've ever seen an ion exchange column, but an ion exchange column is packed with tiny beads of resin. Resin is a kind of a liquid that comes out of trees and it hardens. Okay? And what they do is they pack the surface of the resin beads with sodium ions. Okay, so you notice this little resin bead here has 6 sodiums. Now, as the hard water flows over these resin beads containing the sodium, the calcium goes on to the bead and kicks out, if you notice, 2 sodiums. So 1 calcium takes the place of 2 sodiums. So this calcium will go in here and these 2 sodiums are lost, meaning that you are exchanging 1 calcium for 2 sodiums. So one of those for 2 Na+. So there is a relationship of 1:2 between the calcium and the sodium. But over a while, the next one will come along then, and this next calcium will go in here. And that means that these 2 are removed. Okay, so they're given out. And finally, you'll have a calcium that will come in here, and these 2 are lost. So what do you notice? Over time, the resin bead becomes coated in calcium. So therefore, if I continue to bring in calcium, it'll simply bounce off and the water will become hard again. So what we have to do in order to replenish the ion exchange is we have to wash the resin beads through with salty water, and that reverses the process. It kicks out the calcium and it replenishes the sodium. Okay, so listen to that again. Ion exchange resin, and this is what we call cation exchange resin. They're positive ions. The calcium flows in over the bead. 1 calcium sticks, 2 sodiums are eliminated. Okay, so therefore the sodium enters the water. For every calcium that sticks to the resin bead, 2 sodiums are lost. Eventually, we're going to have a situation where the resin is now coated with calcium. So as the calcium flows through, we're going to have no more further ion exchange. So therefore, the water will go back to being hard again. So to reverse the process, we rinse all of the resin through with salty water. All the calcium is kicked out, the beads are recharged with sodium, and we can use the resin again to soften the next batch of water that's entering the house. But what about deionizing resin? Now this is an ion exchange resin that contains 2 types of ions. Okay, it holds both H plus and OH minus. So there's bead number 1 and here's bead number 2. Now if any of you have seen these, they're normally different coloured beads. You can tell by looking at the resin what it actually contains. Okay, so this bead holds H pluses and this bead holds OH minuses. Now please remember that you're going to exchange like charge for like charge. So the calcium in the water will be exchanged for 2 hydrogens. So the calcium will come in here and the 2 hydrogens will be replaced. Okay, and likewise the SO4 will come in here and be replaced by 2 OH minus. So all of a sudden we've got H plus being eliminated from this bead, we've got OH minus being eliminated from this bead. What will they do? They will meet one another on the way out. They'll combine as they do to form water. So this is a situation where we have deionizing resin. In other words, ions come in but only water leaves. Okay, it's a little bit more expensive than the cation exchange where calcium comes in and sodium leaves, so you still have ions in your water. Here the calcium comes in and is replaced with H plus, the SO4 2 minus comes in and is replaced by OH minus, but then the H plus and the OH minus combine together to give you water, which means that your water coming out of this resin is completely deionized. That means vacant of any ions. So where do we have hard water? Well, most of the hard water regions are from Leinster right across to Connacht and up into Ulster and down into Munster. There's only very, very small parts of the country that are soft water. The very northwest and the southwest. They're the only regions where really natural water flow is soft. Okay, for the rest of the country, we've got hard water. Now you might say to yourself, well, I don't have hard water coming into my house and I live in Dublin. Exactly, because your water has been treated, previous section, your water has been treated to remove the calcium and magnesium before it even gets to you. Okay, and that opens up the whole argument. You know, people say we should get our water for free, but if they're doing so much treatment to give us water that's fresh and safe, and then they're taking the water back from us and cleaning it before they discharge it and send it back to the environment, really, surely we shouldn't be getting that for free. We should be paying for the cleaning of the water that's provided to us. Anyway, that's a political argument. I'm not going to get into that here. But the water that comes into your house is coming from a hard water region. But it's not hard coming into your house because the council have already dealt with it and they've removed the rogue calcium and the rogue magnesium. So is there any benefits to hard water whatsoever? Well, there is. And I've mentioned one already. Hard water contains calcium, which is good for bones and teeth. Okay, but there are 2 other things. People will tell you that hard water has a nicer flavour, all right, and that's because of the dissolved calcium. And also, when you use hard water to brew, be it wine or whatever, or beers, and tan leather, they notice that the beer has a far better taste and the leather is of a far better quality. So therefore, there are very good advantages to using hard water. The physical advantage of bones and teeth being strengthened. Secondly, the taste of the water is improved. And thirdly, if we are brewing beer or making wine or fermenting anything, it gives it a richer flavour. And if we're tanning leather, which is the process of leather treatment, taking the hide of a cow and turning it into something that's wearable, then the leather is of better quality if it is tanned with hard water over soft water. What are its disadvantages? Well, its disadvantages are obvious. First of all, it blocks pipes and makes heating equipment less efficient. All right, it's wasteful with soap because don't forget the first couple of minutes the soap is trying to take the calcium out instead of forming a lather. It's only when all the calcium is gone that the soap begins to bubble up. Okay, so it's wasteful. And lastly, then, if you use it for making tea or anything else like that, it produces a scum on the top, which a lot of people find distasteful to look at, and it puts them off drinking it simply because of its appearance. Okay, it's kind of a light brown appearance and it floats like a crust on the top of the tea or the top of the water that's there. Okay, so you have to know those advantages and disadvantages of hard water. So this section finishes off with a titration. Now, unfortunately, we're not in school. Hopefully, we may be back soon to do this thing. But this finishes off with a titration. A titration which will allow me to give back the concentration of hardness in water in parts per million. But I just want to preempt this by saying that we already now know that there are 4 things that can cause hardness. Calcium hydrogen carbonate, magnesium hydrogen carbonate, calcium sulfate, magnesium sulfate. Okay, so which one of the 4 is it? As a chemist, we're not interested in the 4 separates. What we say is this: all hardness in water is due to the fact that limestone is present in the soil. So we blame all of our hardness in water on CaCO3. So we're not caught up as to whether it's a hydrogen carbonate or whether it's a sulfate. What we're saying is this: the reason why water is hard is because it has gone through limestone. So therefore we blame the limestone on all the hardness. So CaCO3 will always be what we're trying to work out the concentration of in a water sample, just before I go and show you one of the questions. Okay, what do we do? For the sake of analysis, as we've said already, CaCO3 is taken as the sole cause for hardness in water, calcium carbonate. What we put into the burette is called EDTA. Okay, now, unfortunately, for examination purposes, you do have to know what EDTA stand for. And I have it down here. Ethylene diamine tetraacetic acid. That's EDTA. They could simply ask you a question, probably question 4, one of the short questions. What does EDTA stand for? Answer: ethylene diamine tetraacetic acid. And you've got to know what it is. So please, please, please learn what the letters EDTA stands for. And it's a solution which you put into your burette at a certain concentration. You put your water into the conical flask with the indicator, and, which you're going to talk about, a buffer solution, talk about that in a moment, and you titrate as normal. You wait for a colour change, and when you get a colour change, you take the reading from the burette and you do the calculations in the normal fashion. So it's a regular titration, okay? There's your EDTA complex. There's the molecule of EDTA. Now, here's what I want you to notice. Do you see these two oxygens here? The two O minuses? They're like a pair of pincers. Because what happens is, when there's calcium in water or magnesium in water, the Ca2 plus lodges perfectly in there. So one molecule of EDTA will catch one calcium. So there's a one-to-one relationship between the two substances that you're titrating, the EDTA in the burette and the calcium in the conical flask. Okay, it's a one-to-one relationship, which is a lovely thing for our calculations, because then there's no N1 and N2 in our formula. All right, and again, likewise, it could be magnesium in here as well. But the key thing to remember, it's a one-to-one relationship between the calcium and the EDTA, and that's the reason why, because the calcium ion lodges in there, and then the two minuses like that, and the two pluses cancel, and you've got the calcium being carried away in complex form with what was the EDTA molecule. The indicator used is called solochrome black. Now you've got to remember that. There's another version of this indicator which is called areochrome black tea. Now I don't care which one we want to use. You can use areochrome black or you can use solochrome black. Okay, areochrome black tea or solochrome black. I would just prefer you to think of solochrome black, but it's up to yourself. Both of them are in the book. Totally up to you as to which one you want to remember. But I'm going to use solochrome black here just because there's nothing to remember. There's not three things. The solochrome black, end of story. So that's your indicator. Now, when you put your indicator into your hard water, the indicator, as we already know from previous indicators when we were doing pH in indicators, the indicator will only work within a certain pH range, okay? And the best pH range for solochrome black is a pH of 10. Now we know that water is normally pH of 7 or in and around pH of 7. So if we want this titration to work properly and we want to get the two colour changes that we need before and after the endpoint, we have to make sure that the titration is carried out at a pH of 10. And in order to do that, biologists, you'll understand this, we've got to use what's called a buffer solution, okay? And a buffer solution is a solution of a set pH which is used in the conical flask to make sure that the environment of the titration allows the indicator to change colours perfectly. If we don't put this in, we don't get the colour change. It's as simple as that, okay? So, three things to remember. EDTA, ethylene diamine tetraacetic acid, into your burette. Number 2, the indicator solochrome black. Number 3, the buffer solution, pH of 10. So what happens when we do this thing? Now, there's a video down here. You can watch that yourselves. The slides are already up on Google Classroom, so you can go into the slides, click on that. It'll bring you through the experiment. Okay, it'll allow you to see the colour change as well. But what happens is this. When you put calcium into solochrome black, when solochrome black finds the presence of calcium, it goes wine red. Okay, and as you begin to titrate and allow in the EDTA basically takes out all the calcium until there's no calcium left. And when there's no calcium left in the conical flask, the solid chrome black can no longer remain wine red, but changes to a royal blue. Now here's the problem. Dark wine red to a deep royal blue. It's a very, very difficult endpoint for the human eye to see. So we've got to swirl and we've got to turn the conical flask to see if we have reached that. You'll see it in the video. It is worth watching it. You do have to watch it because it is a prescribed experiment. So I would ask you to watch that video before you watch what I'm about to do next, which is the calculation for one of these experiments. Okay, so let's take a sample question here. And again, it's a normal titration, so we don't expect any surprises. The total hardness in a water supply was estimated by titrating 50 centimeters cubed, so there's V1, of the water with a standard solution of EDTA. The ions that cause hardness and the EDTA ions react according to the following equation. Now, as I told you before, in every question involving a titration, a balanced equation has to be given. What are they telling you? The hardness is this one, and the EDTA is this one. All they're trying to tell you is a one-to-one relationship. That's all they're trying to tell you. Okay, you're not going to be using any of those funny ions for anything. It's just a one-to-one relationship. The average volume, so that's V2 here. Where's it? The average volume of a 0.01 molar. So there's your molarity of EDTA, it's M2. Required to react with 50 centimeters cubed to the water. We had it already. It's V1. Was 9.3. So that's V2. Okay. So you've got everything you need in order to do this question. Number one, calculate the average number of moles. Now we know already that moles is equal to the volume in litres multiplied by the molarity. Okay, so all I've got to do there for the EDTA is get its volume in litres. So 9.3 centimetres cubed divided by 1,000, because don't forget there's 1,000 centimetres cubed in a litre. Okay, so 9.3 over 1,000 multiplied by its strength, 0.01. All right, because they're asking me about the number of moles. The number of moles, by the way, it's the first part of your equation. V1 M1 over N1 equals V2 M2 over N2. The V1 M1 and the V2 M2, they are the formulas used for the number of moles. Okay, and because it's 1:1, well then you've got no N1 and N2. So you just multiply M2 by V2. That's all you do. Multiply those two together. And let me do this quickly. So we get 9.3 divided by 1,000 and multiplied by 0.01. And we end up getting, it's going to be tiny because we're dealing with something that's naturally occurring in water. We get 9.3 by 10 to the power of, now minus what? 1, 2, 3, 4, 5 moles. Okay. So the average number of moles that's used in the titration is 9.3 by 10 to the minus 5. Now they're asking me, well, if that's the moles of EDTA, what are the number of moles of M2? Well, it's a one-to-one relationship. And if it's a one-to-one relationship, it's exactly the same. So since it's 1:1, then 9.3 by 10 to the minus 5. So now what they want me to do is they want me to get the total hardness of water expressed in grams per litre of CaCO3. Now please don't forget that this is the number of moles in 9.3 centimetres cubed. Okay, so you've got to be careful that you understand what we're doing in terms of this thing. That's the number of moles. We've got to bring it up to the number of moles in a litre and then go to grams in a litre. So that's something that you've got to take with this 9.3 by 10 to the 5. So let's do that first. This is 9.3 by 10 to the power of minus 5 moles in the titration, in the 50 centimetres cubed of hard water. Sorry, 50 centimetres cubed. So in 50 centimetres cubed. So what do we want to do? I want to go to grams per litre. So first of all, I'm going to multiply by 20 to get it up to a litre. So I'm going to multiply that by 20 as well. So 9.3 by 10 to the minus 5 by 20 comes out as 1.86 by 10 to the power of 1, 2, 3, minus 3 in 1 litre. And the last thing I want to do is turn it into grams of CaCO3. Now Ca is 40, C is 12, and O3 is 48. So that gives me lovely 100. So I'm now going to multiply it by 100 grams to get it into grams per litre. So 1.86 by 10 to the minus 3. So what's that? 0.00186 by 100. And that comes out as 0.186 grams per litre. Okay, So that's the first answer. That's the answer to part 3. And the last thing it wants is the total hardness of water in ppm, parts per million. Now, can you remember what parts per million is? If you can't, they actually tell you. Parts per million is milligrams per litre. So what have I got over here? I've got 0.186 grams per litre. What do they want you to do? They want you to give it back in milligrams per litre. So you're going to multiply by 1,000, because there are 1,000 milligrams in a gram, which will give you 186 milligrams per litre, better known as 186 ppm. And that's the second answer. Now you can review this video as often as you want to go through those calculations, but the calculations for this type of titration are very, very straightforward. So I'm going to stop. That's that part finished. I'm going to ask you, please, if you see down here, now attempt page 328, questions 19.3 and 19.4. So after you've watched this video and you've got to hang with what's gone on in terms of the hard water and the titration, I want you to try 2 questions yourself, which I'll check with you in the live class when we do the live class on Friday, to make sure you understand the processes involved in that simple titration.